purity.
Okay, thank you. So thanks for the invitation. Now I will introduce our recent work of electrically tunable antiferromagnetic resonance in nickel oxide platinum heterostructures. And I'm the presenter, Xu Chang, from National University of Singapore. I will go through the content, and I will start with the introduction of nickel oxide antiferromagnetic resonance. So nickel oxide is a widely known antiferromagnet, and the NiO temperature of nickel oxide is around 523 K. So nickel oxide has an in-plane ferromagnet coupling, and between plane and plane, they are antiferromagnet coupled. So from our VSM measurement, we can see it has shown a compensated antiferromagnet phase. So the resonance frequency is measured by Raman measurement, and the frequency shows to be 1 terahertz, the peak around here. So the high NiO temperature and high resonance frequency has providing the nickel oxide a potential terahertz application at room temperature. So that's why we are interested in this nickel oxide single crystal. So then we have shown electrically tunable Raman spectra in this nickel oxide single crystal and platinum heterostructure. So we have deposited this platinum wire on top of a nickel oxide 111 single crystal, and then we measure the Raman spectra of this at the center of this device. The resonance frequency can be calculated as a function of the exchange field and anisotropy field. So the frequency at room temp at no current is shown to be around 1 terahertz. But with the frequency, the frequency change with our injecting current, and it goes through a redshift. You can see the peak goes through a redshift. And so our next question will be, what caused this redshift? So there can be quite a lot of factors. For example, the Joule heating and SOT and some phonon-mediated process. So we have calculated the spin-orbit torque effect with some reference methodology. So the calculated SOT effect seems not so dominating in our experiment, so which can be seen as negligible. But calculation is just calculation. We have also done some control experiment to illustrate the dominating mechanism. So we have first conduct a platinum device, compare the platinum device, which is shown before, with copper device. The platinum is known to have a strong spin-orbit coupling, but copper, which is known for weak spin-orbit coupling. So the nickel oxide copper device test shows also this monotonically decreasing spectra. So which shows the exactly trend and with previous shown data of the platinum device. So this has eliminated the possibility of the SOT tuning. So then we conduct a temperature-dependent measurement. When we increase the temperature, we can see, oh, the frequency is actually decreasing. So which give us some hint that the redshift of the resonance frequency is actually caused by the Joule heating. Then we also fabricated this cross-shaped device on top of the crystal to double confirm whether this is connected with some phonon-mediated process. But it shows like the frequency shift is independent of the crystal direction, so which eliminated the possibility of phonon-mediated device mechanism. So we have get our conclusion that the dominant tuning mechanism is Joule heating. After confirming the dominating mechanism, we have used this to show electrically tunable terahertz transmission. So this is a schematic of our experiment. We use two lasers with close frequency, and they go into a photon mixer, so it will emit the terahertz, and then the terahertz can be transmitted across this sample and then detect by our terahertz detector. So we can see when there's no current at the right side, it shows a dark peak around 1 terahertz. But with the current, the frequency peak shifted to 0.95 terahertz. So with injected current, we can actually tune the terahertz transmission spectrum. So based on this, we have developed a prototype of a tunable terahertz transmission. So here if our injected current shows a square shape, so we can tune this two channel of resonance frequency of 1 terahertz and 0.96 terahertz. So as you can see here, if the current is off, then the channel 1 will be on and channel 2 will be off. When there is current, the channel 2 is on and channel 1 is off. So this can be a prototype device of a tunable terahertz transmission. So then I will give a summary of our recent work. We have shown the electrically tuning of Raman and terahertz transmission in nickel oxide platinum antiferromagnetic heterostructure. And we have also shown a monotonically decreasing resonance frequency with increasing current. Dominating mechanism is confirmed to be Joule heating based on our theoretical calculation and control experiment. And at last, we have shown a prototype device of tunable continuous terahertz transmission. So that's it. Thank you.
Thank you for the talk. So let's move on to the question and comment session. Now we have the 5 minutes question time. So does anyone question, comment? If you have, please raise your hand, and I will make you unmute. Okay, so I have a question. Okay. Don't raise your hand. Raising hand. Please ask.
Yeah, apologies for interruption. I had would it be possible to go over the nickel oxide antiferromagnetic? Yeah. Could you explain the 111 planes, the effect between them, and how your results could be interpreted in this way, I guess? Yeah.
So we can see the nickel oxide lattice is actually we can show the 111 direction is from is this plane. This plane. So this in-plane shows a ferromagnetic coupling. So all the spin are aligned to one direction, and the antiferromagnetic coupling between this plane is antiferromagnetic coupled. So actually, our result is based on a 111 direction nickel oxide. So the surface of our device will deposit on this 111 plane. So then the our injected current is parallel to the spin alignment. And for our terahertz transmission, this is actually a bulk effect. So because our single crystal is 1 millimeter thin, so if we inject a DC current, it will soon come to a uniform temperature. So the nickel oxide lattice is actually heated. So the terahertz transmission at the exact point should behave as a antiferromagnet, because it is not determined by the interface. Then it is actually caused by the bulk, the antiferromagnetic coupled bulk. I'm not sure whether I've answered your question.
Okay, I will give it. Okay, you can talk now.
Yeah, thank you. Yes, you did. Thank you so much.
Okay, thank you.
Is there any question? Or if you have, please raise your hand. Okay. For me, I have one question. I might be missing something. So what is the origin of the frequency shift due to the Joule heating? So I mean what is changed by the Joule heating?
Oh, I see. I think we haven't get the origin of the redshift at this point, but I have some intuitive explanation for this, because the temperature can actually affect the exchange field and as well as the anisotropy field. So because this material has a NiO temperature, so we can see that above a certain temperature, the exchange coupling will be smaller or stronger. So the temperature can actually affect the effective field. So that's why I think the resonance frequency can be tuned with the temperature, because the coupling can be affected.
Okay. Yeah, I got it. Yeah, thank you for the talk.
Yeah, thank you.